In our presentation, we will introduce our own design CPU scheduler. To begin with, for a scheduler to be efficient, we try to achieve four main goals. Firstly, a low total waiting time and low longest response time, because we do not want the scheduler to wait for a long time. Also, we aim to achieve the high priority processes to wait less than the low priority processes. Therefore, important processes can be executed first. Lastly, we want a lower number of switches since it will create overheads to our scheduler. In our lectures, we were taught on two algorithms, first come first serve and shortest remaining job first. And meanwhile, Robin was taught as one of the preemption methods. Lastly, we were taught that when dealing with priorities, queues will appear in multiple layers. Next, to begin with, we will introduce some characteristics of the following scheduling algorithms. First, SJF has the lowest possible total wait time. As for preemption, round robin reduces maximum response time, but at the cost of an increase of switches. Also, having multiple layers of queues grant different priorities.
So, having acquired the understanding of these algorithms from class, we started our design process aiming to achieve a good balance between the strengths of these algorithms. And we ended up on this three-layer mixed queue design. The first queue is a first-come, first-served queue that only accepts newly incoming customers. The two queues below are the self-sorting shortest job first style. They are the high-priority process queue and the low-priority process queue. To prevent starvation, we also implemented an aging mechanism in the low-priority queue. And here is an animated demonstration of how our algorithm works. Scenario 1 is when customers come in. They're all put into the first layer queue and take the CPU in the order they come in. We have a round-robin mechanism monitoring how long each customer has been occupying the machine. Whenever a customer surpasses the allowed limit, we remove it from the machine and put it into the second or third layer queue depending on its priority. Scenario 2 is when a higher level queue is empty and the current process finishes running. We just look a layer lower to find the next process to run. Pretty straightforward. Scenario 3 demonstrates aging and the shortest job first self-sorting mechanism of our second and third layer queue. Say, there's this process that has waited in the third layer for too long. We then move it to the second layer queue. But instead of adding it straight in, we sort the queue and put it in according to its length.
Alright, so these are the performance comparison between different algorithms. For the first come first serve, all the waiting time and response time is kind of long, but after the round robin kicks in, all the waiting time and response time reduce a bit, but the switches increase a lot. When we implement the shortest job first instead, all the waiting time reduce a lot with the same response time and switches as the first method. After we implement the high and low priority queue, the high priority waiting time decreased a lot, but the total time increased a lot too. Meanwhile, in our final algorithm, we managed to lower the low priority queue waiting time and the response time a lot with aging to prevent the starvation. And with that, this is the end of our presentation. Thank you.
Thank you.